Alright. Simpson's paradox is something that happens when you incorrectly add across two variables. Simpson's paradox does not always happen, but sometimes it happens. And so I want to show you some examples of an example of when Simpson's paradox happens. Okay. This first one has to do with baseball. Let's actually look at this second table on your baseball page. So, do you know that in baseball, a lot of times, I mean, I can't imagine when it is in this way, but most of the time, your rate against a left-handed pitcher is going to be different from your success against a right-handed pitcher. Correct? Okay. And then, you know that a lot of times when you go up to bat, and they'll display what your overall batting average is. Okay? Well, let's look at those things. Let's look at those things. For a left-handed pitcher, let's look at player A. This 28 divided out of the 81 times it bats means that this player has been on base or made a hit 35% of the time. So 0.35. Okay, we're just going to do it in percent. Okay, and then here, what are you saying? I would imagine so. Okay. Doesn't matter. No, we're just, no. Okay. Next. 12 out of 32. Player B. Okay, here we go to the facts. We're not talking about confounding the study and yada, yada, yada. 12 out of 32 is a percent of 38%. So against left-handed pitchers, who's better? Against left-handed pitchers, I would send player B to the plate. Now, right-handed pitchers, 5 out of 22 is 23%. And 33 out of 119 is 28%. So, for right-handed pitchers, which player is better? Okay, so in both cases, against the pitcher left to right, whichever pitcher comes in, player B is the better choice. However, when these things get added across for the total, let's look at your total overall batting average. For the first one, player A, it's 32%, and for the second one, it's 30%. What? Which one, just looking at the overall, seems to be better? A. So that is called Simpson's paradox because when you look at these items individually, you have one conclusion, and when you look at it as a overall, you have another conclusion. And here's how that happens. I know that when the commentaries are talking and the guys coming up, I hear them more talking about against righties or lefties as opposed to the overall. Now, they'll post the overall, okay, but I hear them discussing more this. I mean, that plays into more the choice of who's coming up to bat, whoever they send in to go bat. Now, here's how that happens. Watch. For player A, let's just look at player A. Player A had left-handed, against left-handed pitchers, was doing that. Against right-handed pitchers, was doing this. And according to the way that this was completed, they are adding it up and saying that it's comparable to the 33 over the average of them is going to be the 33 over the 103. Is that the way that you should add fractions? Okay, no, what's happening? You don't add with different denominators, so that is where the math gets messed up, okay? Because you are adding across two variables, and if you didn't come up with a common denominator, then that's going to be messing up with your information. So what happens here is pulling data together. When you put things together, it loses the important information and sometimes leads to the wrong conclusion. It does not always, but sometimes it does. And those times that it does switch the conclusion, it's called Simpson's paradox. It's happening because of the inappropriate math of adding across the two variables. Yes. Next, I'll show you a couple other examples. Here we go. This is the best well-known example. This happened in 1973. It's actually a court case that went all the way up to the Supreme Court. The University of California at Berkeley was being sued for bias against women admittance into the graduate schools there. So what happened was they were saying that of all of the men and women applicants and the admittance rates, that women admittance rate was significantly different than the admittance rate of men. But what happens is when you look at the individual departments, because you go to the college at whatever you choose to major in. So if you're majoring in like arts or business or chemistry, I don't know what else. Okay, so look at what happens. This first one says there were 825 applicants in this and 62% were admitted. However, of the 108 women applicants, 82% were admitted. So in fact, which gender had a higher admittance rate? Women. The same thing with the second one. Here we had 63%. So here we had 63% admitted in that college as opposed to 68%. So women had a higher admittance rate. Now, in this C category, 37% to 34 men were higher. Women were higher here, men were higher here. So in actuality, 4 out of the 6 categories, women had a higher admittance rate, and so then the court case got dropped, and it was rectified and said that they were not actually biased against admitting of women in graduate school. Okay. So what I want to do is look at the problem that you're going to be doing on your homework, and your homework, just FYI, so that you know, your homework is going to be including all the 4 problems, one of which you just finished, the 4 problems on this, plus I want you to also do the warm-up. So you picked up the warm-up also, which I don't have a thing of this. Because ideally, and this may be just like being wishful thinking, ideally I would like to come in tomorrow, go over these things, and you're successful on them enough that we can do a quiz over them, of which the quiz will be in the form that your warm-up is. So you'll look at your warm-up, and if you're still successful about something like that warm-up, of course, then you are going to be successful in the concepts of these chapters. I would like to do that. I'm not guaranteeing it. Hey, I know that we are going to be finished here in just a minute. Like 2. Okay. There you go. Okay. All right, so read through these problems and do those all. Thank you.